So I'm going to give a bit of an overview about sort of what the present day ice sheets are doing and the different processes that are affecting those. And this is work, I've got a long list of co-authors I've been privileged to work with on this, and actually that's only a partial listing. There's actually several more people I should have probably added. Just to put things in perspective, this is the impact of a 1 meter sea level change. This is fairly well-used figure, but this isn't a Democrat and Republican map of Florida. It's showing the inundation of the South Florida coast due to just a 1 meter level of sea level rise. And the IPCC comes out with something like 20 to 60 centimeters potential sea level rise over the next century. And the ice sheet and glacier contribution to that is something like 4 to 23 centimeters. To put that number in perspective, the current rate just from the ice sheets right now is about right in the middle of this. It's about 10 centimeters per century. Well, in doing this estimate, while the IPCC was working on this, all sorts of things started to happen on the ice sheets that we really didn't understand and were quite startling. And none of these were included in the best ice sheet models that went into this prediction. And of course, the IPCC has to go with the established literature, and so they were more or less put into a position where they were forced to conclude that there's really no upper bound that they could, reasonable upper bound that they could formulate for sea level rise over the next century. And this is all due to uncertainties in glacier basal conditions, the amount of ice deformation and the interactions with the surrounding ocean. All of these basically limit our ability to make accurate projections. There really is no accurate projection. These numbers are just what they were able to glean from the literature based on the state-of-the-art models at the time, but that are missing many of the physics and can't reproduce many of the changes we're seeing. Basically, an ice sheet sheds mass to the ocean through a couple of different processes. One is direct surface melt. This is what the public normally thinks about, ice sheets just melting down and the water running off into the ocean. But of course, they also discharge ice across the grounding line in the form of icebergs, or they float as ice shelves where they made their contribution to sea level at that point. Again, this is direct surface melt. This is what people tend to think of. You get these beautiful melt streams running along the surface of the Greenland ice sheet. And about half of the annual mass loss in Greenland is due to, even the steady state annual loss, is due to direct surface melting. Antarctica, though, is so far south that there's almost no surface melt outside of the peninsula. There's a few melt events go through, but there's no real actual loss. That melt refreezes in the firn and doesn't really go anywhere. To give you an idea of the magnitude of the melt, this is at 1,000 meters or so on the ice sheet in western Greenland at about 70 degrees latitude. This is one of our GPS stations. And note the crossbars here that we use to brace it here is at the surface of the ice sheet. And here's a similar station. We came back almost exactly a year later, and you can see they're about 5 feet up in the air. In fact, Mark here is holding a piece of fish line that we had drilled a hole into the ice and put the fish line in, and that's how much it's melted out. Now, I don't want to give you the idea that this is how much the ice sheet is wasting away. This is fairly steady state melting. Of course, an ice sheet collects snow from above, and the motion brings it down to where it will melt away. And sorry about that. So the inflow of ice from above is more or less at this point balancing this melt rate with any imbalance being more on the scale of centimeters rather than meters. Mass loss in Antarctica is more or less dominated by the flow of these ice streams. Whenever I show these plots, basically you're looking at speeds of glaciers. Fastest flow in Antarctica here is about 3, well now it's 4 kilometers a year out of Pine Island. So these red colors on this log scale are all sort of 400 or 500 meters per year and above. And the blues are sort of the 1 to 200 meter year speeds. And then the green is more this, brown and greens are more the sheet flow that's slowly flowing out that coalesces into these outlets near the coast. And again, most of the ice it goes into a floating ice shelf, which as far as sea level is concerned, it's made its contribution at that point. But the form of how the ice shelf loses the ice, either through sub-ice shelf melting or iceberg calving, can actually have dramatic effects on how the interior ice behind it responds. So direct melt, surface melting is relatively well understood. There's quite a bit of uncertainties in some of the models, but they're not, no one's thinking they're off by orders of magnitude, like the possibility with ice discharge and iceberg calving and basal melt. All of these are the source of most of the uncertainty in the IPCC, and that's largely what I'm going to focus on today. Most of the ice dynamics concerns relate to sort of two basic processes. One is enhanced lubrication, a slipperier, more lubricated bed, or loss of buttressing. You may have heard the term ice shelf buttressing, but it doesn't always apply just to ice shelves. Any loss of any large section of the ice sheet can give you a loss of buttressing, even if it's grounded ice rather than floating ice. This is a well-used figure from Jay's Wally, and this is one that even I can take to a third grade class, and generally the third graders even get it. And for that reason, this whole surface meltwater and enhanced lubrication has actually been the one that we've heard a lot more about in the press and the New York Times and places, because when you speak to a reporter, they can also get it. So the basic idea is we've got lots of surface melt and presumably more in a warming climate. And if it can make its way through to the bed, and of course the ice is 1 kilometer thick here, and I'll talk a little bit about how we actually get it through that thick ice. Get it to the bed, we get more lubrication, and the ice sheet picks up its speed. And some scenarios, it's been so far as people said to sort of slip slide all the way into the ocean, and there it's gone. Well, we do have plenty of that melt on the ice sheet. This is one of the large melt lakes on the surface of the ice sheet. If you fly from Europe to, or Northern Europe to the US this time of year or back, you may fly over the ice sheet and you may see these bright blue jewels dotting the surface of the ice sheet into these beautiful lakes. This one I think is probably 2 or 3 kilometers wide at this point. I think this is when it's a stage when it's filling, and it actually got to be about 4 kilometers long when it was completely full. We also get these beautiful, sometimes the lakes fill their basin and then they overflow, and the melt carves these beautiful channels. This was one of the more spectacular ones, probably the biggest one, and it's something like 60 feet deep here as it runs away into a crevasse field. So we want to get this water from the surface to the base of the ice sheet, if it's going to have any effect. And theoretically, this is fairly easy to do. If the water can find a crack, and the crack's deep enough, the water, of course, is denser than ice, which is why icebergs float. And if you can maintain this crack, keep it full of water, not let, say, the crack propagate a little bit and have the water level drop to equalize the pressure. But if you can keep it full to the top, overflowing here, you get a higher pressure at the base of the crack due to the higher overburden of the water, and it wants to wedge the ice apart. And whether the ice is 1 kilometer, 10 kilometers, 100 kilometers, if you can keep enough water in that crack, you can hydrofracture all the way through. And in fact, this is a 3 kilometer long crack the day after about a 3 or 4 kilometer wide lake drained fairly abruptly. So one investigation we had on the ice sheet was to actually try and understand how these lakes drain. It's easy to do in theory, but there were many of sort of glaciologists out there who didn't believe that this actually, I mean, 1 kilometer thick ice is still a lot of ice to have to break all the way through. Just looking at a little bit of what happens after these cracks form. This is a lake where it drained just a few hours before, and of course the crack will immediately close because at that point it's full of air and the overburden will want to close it most of the way. But there is still water flowing into the crack from the melt streams that were formerly feeding the lake. And there's sort of discrete points where those streams feed into the crack, and then you're dropping this water through 1,000 meters, so there's plenty of energy and turbulent flow in there to actually keep this hole melted open through the rest of the summer. So you get sort of this evolution here where here's the crack, it's closed up and right afterwards. And then this is a couple days later and the melt's starting to sort of widen the hole. And here's an old hole from a previous lake drainage where there's no water flowing in, but you get this beautiful circular hole, and it goes down about a couple 100 feet before the overburden of the ice sort of pinches it shut at the bottom. And here's an actively draining large moulin that we flew over in the helicopter. And these things, you can't see the bottom, they just go straight down. So one of the things we did to investigate rapid lake drainage was instrument a couple of lakes. We were fairly naive at this point. We knew they could drain in a day or two from satellite images, but not quite how fast they could drain. Needless to say, we don't use the boat anymore. But at this time, we were lucky, and we went out and we hovered over these holes and put in the pressure transducers in the lakes, and we put GPS on the shoreline. And a couple weeks later, so this is day 196, mid-July, and this is the record here. There's 3 different curves. There's a gray curve here, which is actually the lake level dropping off, and we're looking at this green box zooms in on a 90-minute period here. The black curve is the GPS on the shoreline, and this is just a vertical elevation, and it's not referenced to 0, so it's showing about 1.2 meters of uplift. And then the red curve is showing the uplift rate. And basically what you see is as the water level drops over this 90-minute period, peak uplift rates at the time of peak drainage, and you also see this surface rising up by about a meter, and again 1.2, 1.3 meters. Basically what you're seeing is the water filling the void underneath the ice sheet where it's drained in and it's kind of blistered up and raised the surface of the ice sheet. And for the one lake we were there, we were actually at the shoreline when it drained. It was in the fog, so we couldn't see the actual drainage. We just saw the water line recede out a little bit, but it was quite an interesting experience because the whole surface is kind of, sounds like a bowl of Rice Krispies. It's snapping and crackling and popping, and you're not really quite sure where you should go. But fortunately, we knew from this past data that everything would probably be okay. This is just showing a map view of what the GPS is doing, so east and west, or east and north here. And you can see it picked up the speed. This is sort of the daily motion vector here in day 210. It was a little bit faster, but you can also see this excursion here off to the side of the flow path. And basically what you're seeing there is the crack opening up. So the crack opened and the GPS moved away, and then this time here corresponds to about the peak drainage time here. And then as the water receded, the crack closed again and the ice moved along as it had before. And so this large, almost 6 kilometer square kilometer area lake that was 40 feet deep drained in about 90 minutes. And the flow, when you calculate the flow rate, it's actually more than the flow over Niagara Falls, so it's quite an impressive event. So we know it reaches the bed, so then the question is, how does it affect flow? A lot of the work, again, I do is using the satellite radar techniques to measure the speed of glaciers, and we're able to do that over wide areas, and this is an area in Greenland. I think there's actually scale bars on the next slide, but it's about several hundred kilometers long. This is Disko Bay up here. This is Jakobshavn Isbrae, the largest glacier in Greenland's west coast. And you sort of have this region of slow-moving sheet flow almost all along the southwest coast. And then to the north of that, you have several outlet glaciers. So this is more like the regime that the ice sheet models model, basic sheet flow without much going on. And these are these narrow outlets that discharge large volumes of ice. The width of this Jakobshavn, which is throwing out about 30 cubic kilometers or more of ice a year, is 5 to 10 kilometers, and a typical model resolution might be 20 kilometers. So it's not even able to resolve these ice streams. If we take this 3-year mean velocity that was put together from some 70 different sets of radar observations, and difference that with just one of our summer estimates, we see here over on the rock, everything's a nice yellow color, which is 0, and that's what we'd expect. And but the data are a little bit, the radar techniques have difficulty in the summer with melt, but basically where it does work, we see quite an extended area of faster flow here. And this is showing that the flow is about 30 or 40 meters a year faster. In fact, on the areas of ice sheet flow all along here, it works out to be about a 50% speed up over this 24-day period that the radar was monitoring the ice speed. But more importantly, we see on the outlet glaciers, it's only sped up by about 10%. And actually, I didn't even include Jakobshavn in that analysis. If you include that in there, it's actually a much smaller percent than 10%. And the significant thing about this is when Jay Zwally first saw the speed up at Swiss Camp, he was getting percentage speed ups, and people wanted to apply a percentage speed up to the ice sheet. And instead, we're seeing more, there's just an absolute speed up of 50 to 100 meters a year, which for the ice sheet is a big percent speed up, but for something that's moving 10 kilometers a year, a 100-meter-a-year speed up is nothing. So really, we don't seem to have to worry too much about this lubrication effect running away and causing it just to start disgorging a lot of ice into the ocean. Certainly along this part of the ice sheet, the modeling that Byron Parizek has done shows that it's definitely an effect that needs to be adequately modeled, and these parts of the ice sheets will be affected by it, but it's not the kind of order of magnitude change that people have worried about. I'll just zoom in on our two North Lake and South Lake sites here. Those are the two sites we instrumented. The record I just showed you was from the North Lake, and I'll just briefly show you the GPS record from both of those lakes. And you do see that it does correlate very well with melt. Essentially, I've compressed the winter axis here, so its time has been scrunched up a bit here, but everything's pretty constant in the winter. And you see the enhanced velocities at this part of this summer and in this part of that summer, and several spikes. Some of them are lake drainage events and the Moulin opening here, but many of them correlate over the 20-kilometer distance between the lakes. And they also correlate very well with these black and gray curves, which are the positive degree days just estimated from the weather stations we put at each lake. And so those serve as our proxy for melt. And you can see this big melt event here, for example, corresponds very nicely with this big speed up events here. And we only had one GPS station working this particular summer, but you could see there's two melt events, and they correlate quite well with these speed up events. So the ice sheet is very definitely responding to melt, and some of these are much greater than 100% in very short transient times. We get, for a day or two, we actually get speed ups, almost five-fold speed ups. And there have been cases where other people have recorded even larger brief speed ups. But when you integrate it out over the course of the summer, it's a much smaller change. And then when you factor it in over the winter too, it becomes even smaller. So that was sort of the surface melt effects. Now I'll talk a little bit about buttressing. And to do that, I'll just use this sort of cartoon ice sheet, a sort of typical parabolic ice sheet profile. And let's just imagine we can vaporize away part of the ice sheet instantaneously, and we get this cliff here and this big pressure gradient here. And the ice is going to really want to flow out here. And of course, ice is viscous material, so it's going to want to respond to this with higher strain rates here to transmit the stresses back onto the base of the glacier up here. So when you lose stress down glacier here like that, the glacier has to respond by speeding up to redistribute those stresses inland through the strain rates you get from the speed up. Well, it's pretty, and in many ways this is not so different than, here's the buttress analogy. You kick the buttress out on this church and the wall falls down, and more or less the same thing happens on the ice sheet. Well, of course, if this were a real example and it was grounded like this, the ice sheet's going to take some time to melt. You can't just vaporize, and leave a several hundred meter cliff here like that. That's not going to happen on a land terminating glacier. But it can happen when you bring the ocean into play and you have a way to get rid of the ice rather quickly. And that's what happens with tidewater glaciers. Often they're perched upon some nice stable little slope here, and then they can start, if they start calving too much and they calve down the backside of this, they tend to retreat back, and they can, in a given summer, some glaciers can lose 7 or 8 kilometers. Some beyond from where they would normally be positioned at the end of the summer, they can retreat back, and that leads to big speed ups and a lot more extensional flow, much more stretching and potentially more thinning, which can then, of course, lead to more thinning and more calving, and you can get a runaway process if the geometry of the ice sheet is such that it'll let that happen. Typically, things do tend to often, they'll find a new high spot and restabilize there for at least the short term. And that this effect, this pressure gradient here kind of goes as h squared, the thickness squared, and this drag again has to be redistributed upstream. So many of Greenland's tidewater and outlet glaciers have accelerated by 50 to 100% over the last several years. And these are the sorts of dramatic changes that prompted the IPCC to say, we really don't know what's going on here. We're just going to have to put this little asterisk on our estimates and explain that we really don't have the knowledge to provide an upper bound yet on these estimates. Just to give you an example of one of these, this is Jakobshavn Isbrae. Again, this, I don't think I have a scale bar in here, but this is about 15 kilometers, and this is the floating ice tongue it had that was stable at this position for about 40 years. And then in the late 90s, it started going back and disintegrating and thinning. And by 2003, nearly the whole ice tongue had disappeared. And now there's only a seasonal one that advances each winter, but not anything out to like its former extent. And I'll show an example of that in a bit. This is, you can see, an example of the speed up here. In 1992, the glacier's moving with these cool blue colors, which are about 7 kilometers a year near the calving front here. And midway through the speed up, we're shifting to these warmer red colors, which represent about 10 or 11 kilometers a year. And here in 2006, you can see it's getting up to sort of 12, 13 kilometers a year near the front. So really quite a dramatic increase in speed on this glacier. I don't think 10 years ago, 1992, if you told someone the glacier would double its speed, they would have thought you were some kind of crackpot or something. Just to look at the time series that we have in a little more detail, here again is the Jakobshavn, and here I'm going to zoom in on these points, which I'll show you time series of the speed along those points, and the points have names M6, M9, and so forth, and the number gives you the distance from this position here, the late summer calving front, so 6 kilometers, 9 kilometers upstream. And here's a time series, again at these different points, and at the top here what you see is, well actually let me start on the left, it's kind of a busy figure, but here you're seeing the data I just showed, more or less showing the dramatic speed up with a time compressed scale here from 90 to 03, I think. And then here's a much more expanded time scale here where we're getting estimates every month or so. And so you see that the step increase in speed and then leading up to the speed. And then on the top here I'm showing, this is June, July, August, so this is the summer periods. And what you see is this seasonal advance and retreat of the ice front. And I'll show this a little more graphically in a minute. But what you see is when the ice front has retreated the most into the ice sheet in the summer, that's when you get the peak speeds. So this is really a nice demonstration that the ice shelf is very direct, or the flow of the ice stream is very directly responding to the position of that ice front, and that it's the retreat of that ice front that's driving the increase in speed, and an instantaneous almost increase. You break off the ice shelf and you get an immediate speed up. This plot also illustrates, though, how these effects can propagate inland, because as you start drawing, this is the area that's most affected. As you can see, it shows up right near the front, but you're not seeing that seasonal impact far inland, but you're sucking a lot of ice out of here, and that's steepening the sides in here and here, and ice flow responds to the surface slope, the driving stress. So this sort of diffuses inland, this initial speed up here, and causes more speed up further inland. And you can see that in terms of these roughly 5% per year trends on these, the overall speed up here. So we initially had this dynamic response, and now we're seeing the ice steepening and this more diffusive response into the ice sheet. And this just gives you, hopefully the animation, yeah, so you're seeing the glacier advance over the course of the winter when the fjord locks up with sea ice, and then So it keeps advancing, and then in the summer it advances way back and retreats back. And so essentially in the winter, when there's a lot of sea ice in the fjord, the calving almost completely stops, and the ice front here just advances out at the speed that the glacier's moving, and sort of bulldozing all this sikusak, this mix of sea ice and glacial ice. It just bulldozes it out, and it really doesn't calve. And then as this stuff loosens up as it melts, or just the fjord clears, the strong calving resumes. So of course we have all these processes that we want to now understand what the sensitivity to climate change is, and mostly what we've been focusing on is just sort of identifying the processes that are causing these speed ups. We know they seem to be related to change, and certainly over the last few summers it's been warmer in Greenland, summers and winters, but we don't understand exactly how warmer summers translate into more calving, what the process is. Again, that was the thing about the surface melt enhanced lubrication. The thing that's appealing about that is that more melt just gives you a simple process by where you get more ice motion. But these buttressing changes are a little bit harder to directly relate to climate. For example, more meltwater in crevasses could cause more calving, and the changes in sea ice in the fjord could also have an effect. And that's one of the, I think, the leading causes on, one of the leading causes on Jakobshavn. This is temperature. 5 minutes? Okay. This is temperature over the last 20 years or so, and you see that the winter temperatures went up briefly before the disintegration of the ice shelf, and the sea ice concentrations were dropping. And if the sea ice is slowing calving, when we remove the sea ice early and have the sea ice break out earlier in the spring, and the calving is going to happen more, which is going to lead the glacier to retreat more, and then you get this feedback. Real quickly on ice shelf buttressing, I'll just sort of go over the process and then not say too much about it, but this is the cartoon ice shelf. This is more what we're seeing in Antarctica. If you've got an unconfined ice shelf, which is just one that's sticking out into the ocean, there's no resistive stresses from the water. So you can remove this ice shelf and the ice sheet won't even care. But if you have side drag is calving into an embayment, then when this drag has to be taken up here when the ice shelf falls apart. So more like a Jakobshavn calving in there, and you can get this sort of catastrophic effect when the ice shelf is calved, just like if you remove a little plug from the toothpaste tube here. And of course we've seen that. This is the famous NSIDC, one of the Larsen, actually this shows it preceding the breakup, but you can see all these melt ponds, and this same hydrofracturing process comes into play here. And these are all some more head scan boasted, and you get lots of breakup going on there. And of course there's also sensitivity to warmer ocean temperatures, and I'll quickly go through, I'm not going to go through this for lack of time, but there's basically about 1/10 of a degree warming leads to about an extra meter of melt on the base of the ice sheet. So I just put this up. I thought that somebody was telling me that they got this on one of their proposals, that glaciologists are basically in unanimous agreement that the ice sheet's collapsing. Well, it really depends what you mean by collapsing. I think everyone's in agreement that the ice sheets are losing more mass. It's just a matter of how fast they're likely to continue to lose mass. Sort of a couple of end members are the catastrophic collapse. This would be Jim Hansen taking the 1 centimeter we have now per decade and doubling it every decade to get 5 meters at the end of the century. That's pretty catastrophic, and it's a little bit, you have to actually come up with a process by which you're going to double every decade to get that. The far more conservative thing, which would be, end member, would be just a slow leak. At current rates of sea level rise, the current rates we have now, it's going to take 5,000 years to get your 5 meters of sea level rise. The true answer lies in somewhere in between here, and we really don't know at this point. I suspect it's probably going to be measured in tens of centimeters for this century, but not in meters. But that's like everybody else. I'm just extrapolating from current data there without any real quantitative basis or model to do that. So basically, the IPCC got it right when they concluded we really don't know the answer. So in summary, we basically know that processes, the buttressing is greater than the surface melt. We really need to get this links to climate to be firmed up before we can kind of couple any kind of model, climate model to the ice sheet model. We need to get the physics into the ice sheet models. We're starting to get to kind of 10-year decadal scale records of how glaciers respond, but beyond that, how these big events we're seeing now, how they're likely to fuse into the ice sheet and respond over the next century, we really have no idea. And despite this progress, I think we have made, I think the IPCC uncertainty remains, and it's going to be a while before we really have really finely tuned estimates of what sea level is going to do over the next century. That's it.
Time for questions. I don't know where the microphone is. There it is.
You mentioned ocean temperatures in relation to Antarctica, but did not mention them in the Greenland context. David Holland and colleagues, they have presented data that subsurface ocean temperatures have been increasing since 97, and they might contribute to the West Greenland.
The deep water and the sea surface temperatures have all warmed up in the atmosphere. Everything has warmed up in that area, so it's a little bit hard to say exactly which of those is causing the problems. On Jakobshavn, you can probably argue both. You can argue, like I was arguing here, that it's the loss of sea ice which is related to this warming, but you could also, as David was arguing, is that it's the basal melt beneath that floating ice tongue. It gets more difficult for the remainder of Greenland's glaciers because they tend to be tidewater. They don't have much of a floating ice tongue to melt underneath. So in that case, I think the sea ice hypothesis works better than the deep water because it's hard to get the deep water doing much to the base of a calving front. You've got a glacier advancing at 30 meters a day. It's hard, and you've got melt rates of nothing like that value. So it's hard to actually get much from the ocean in that case. But they're all sort of related. I'm not exactly sure. Like I said, basically the links to climate we really need to firm up.
When you say sea ice, are you actually talking about a physical buttressing from the sea ice at the surface, or are you talking about a correlation that says that when there is sea ice, the temperatures are colder and the ice is stronger, or something like that? Is it the actual sea ice that's preventing a huge calving front from moving?
The calving front doesn't care that the sea ice is there. It pushes in fact, it bulldozes the sea ice in front of it out at the same speed that it's going. But the calving itself, the rolling of these 100-meter wide blocks off and calving, seems to be completely suppressed in many cases when the sea ice is there. I think whether it just can't roll over or the fjord gets so choked that it can't calve new icebergs, I'm not exactly sure the exact process, but it does seem to correlate pretty well. And you can look at calving records for glaciers and you see very little calving often in the winter.
So it's a physical pressure, not a temperature effect?
Yeah.